all the way up to highly classified here and now troubleshooting on space satellites, rockets, ECM systems. It's kind of nice to know that in this world of qualification and modesty and erosion of prerogatives, that in the field of defense electronics, we in the United States are very, very good. I feel myself rather proud to be associated with defense electronics because best. The technology is number one. Generally, if there is a little technological leverage that you have, in defense electronics, equipment and facilities are number one. It's rare that an innovative idea goes for want of necessary facilities or equipment. But probably most importantly, and many times this is not stressed, the people who work in the defense electronics field, in my personal opinion, are number one. I serve on some Pentagon committees, and in the agencies I never cease to amaze myself at the quality that the government attracts in various agency panels that sit in judgment on the defense research. In corporations such as Hughes, TRW, you find very, very good people working on defense projects. And of course in the universities, defense stimulates our finest minds. It's interesting to look at defense and its excellence in terms of an unusual thing nowadays, that of natural competition. We always seem to talk a lot about cooperative efforts and everybody working together using some prototype models we see from overseas. But in my opinion, some of the excellence in DOD capabilities is built on competition, corporation against corporation. Many of the times, Westinghouse and Hughes have worked late into the hours of the night to just trim up a proposal so that one would win over the other. You find competition in universities for grants, for centers of excellence. And finally, you find competition even among agencies. Can you imagine the Army and the Navy competing with each other for a certain program area because they think that they perhaps understand the issues better? This is different than we usually hear, but that type of competition has made us very, very good in defense electronics. And I certainly am proud of being in that field. Today we have three speakers whom I believe understand the excellence that the agencies, industry, and the universities are bringing to that field, and it's my pleasure to introduce those people, and after their talks we'll call for questions from the floor if you have any. The first talk is by Dr. Leo Young, Director of Research and Laboratory Management of the Office of Undersecretary of Defense for Research and Engineering at the Pentagon. Dr. Young was appointed to this position in 1981. Dr. Young earned his doctorate in electrical engineering in '59 at Johns Hopkins, and he was elected fellow, which is the highest ranking honor in our organization, in 1968. Dr. Young, as Dick Gowan, was elected president in 1980 of the IEEE, and as you probably know by now, there are over 230,000 members worldwide of that group. In my mind, Dr. Young has been a source of inspiration to the recent generation of electrical engineers in the field of microwave devices. Besides being president of the IEEE, he has made substantial and important contributions to the field of avionics. It's my pleasure to present to you Dr. Young, who will speak to you on contributions of defense research to electronics. Dr. Young.
Thank you, Harvey. I guess the mic is working now. It's my task this morning to show the intimate connection between electronics and defense. And what I plan to do is to first talk about the developments and the past contributions of electronics to defense, and then go on to some of the new initiatives that are taking place now. Engineering has always been closely associated with defense. In fact, the term civil engineer was invented much later to distinguish that kind of engineer from the military engineer. So engineer initially really meant mainly military type engineer. And one interesting story of that is when Archimedes worked on the defense of Syracuse back in the year 213 BC. If you remember, the Roman fleet had invested the port of Syracuse and was trying to starve it out and blockade it. And Archimedes, helping the king, managed to make some huge mirrors with which he focused the sun's rays on the enemy ships and set them on fire. That was in 213 BC. Now, more than 2,000 years later, we work in such things as high-energy lasers and do much the same kind of thing in a more sophisticated way. So the history really goes back a long way. In particular, electronics has become very closely associated with defense. Now, to recognize the current contribution of electronics, it's interesting to note when you look at the basic research budget in the Defense Department, you will find in the last few years it's been growing above inflation at the rate of about 10% per year, which is just about twice as fast as the average rate of growth of the entire basic research program. This is in electronics and computer sciences combined is what I'm talking about. And that program is approximately 22% of the total basic research program. Nearly the total basic research program of DOD. So clearly it is recognized to be a very important field. Let me go on now and talk a little bit more about the future and what the future holds. There can be little argument that modern technology in general, and electronics in particular, are bringing about radical changes in the face of warfare. The actual battlefield is becoming more diffuse and more dynamic. More and more, human limitations, such as reaction time, are being encountered in the push towards higher performance. There is pronounced tendency to concentrate high value in discrete units, usually platforms. The survivability of these targets then takes on great importance, sometimes leading to a modification of doctrine and tactics in order to ensure it. Electronic technology plays a major role in this volatility, and I believe that we can see in the fast-moving commercial electronics world a more or less accurate to adjust. The lethality of modern tactical weapons is increasing to the point where we find it necessary to operate our high-value platforms more and more remotely from the our tactical command and control systems, which increase very rapidly when the speed of modern weapons and consequently diminished reaction time is taken into account. Inherent limitations in electromagnetic propagation make it necessary to employ remote, elevated sensors. Present-day systems employ airborne sensors, but it seems clear that the future trend will be towards space. We can reasonably anticipate, for example, that by the first decade of the 21st century, we shall have operational spaceborne radars as well as high-resolution optical and infrared imaging sensors. These systems will require major technological advances in a number of critical areas. Perhaps most significantly, the high resolution required will mean generating vast amounts of new data, which will increase the demands and the capacity of data processors and communication links. Similarly, increased data rates will be required for infrared and optical sensors, which will be of the staring mosaic type, rather than today's scanning types. In other words, instead of scanning in time, you will have many, many sensors all staring at the same time in many directions simultaneously. Airborne and spaceborne synthetic aperture radars operating in the microwave range will be needed to supplement optical and IR sensors, which suffer from atmospheric limitations. They don't see through clouds, of course. Synthetic aperture radars generate very large amounts of raw data which have to be processed to form an image, and both solid and synthetic aperture radars will need to employ frequency agility and adaptive beamforming techniques to combat enemy jamming. At the risk of belaboring the point, I foresee an information explosion of staggering proportions on the battlefield of the future. The unprecedented volume of data collected by future sensors will dictate radical changes in the ways that information is processed and disseminated. In fact, the data processors will, in effect, need to participate in the decision-making process. Artificial intelligence, now in its infancy, will be reaching a level of maturity by the first decade of the next century, which will permit its incorporation into many kinds of system. Greatly improved data processing hardware will make intelligent sensors feasible, which, combined with advances in communications technology, will revolutionize battlefield command and control. In addition to advances in signal and data processing and artificial intelligence, a versatile, intelligent sensor system of this kind would require voice recognition, distributed data processing, high data rates, survivable communications, and large capacity data storage with fast access. In the important area of sensors, great strides are being made in improving sensitivity and resolution. For example, using spaceborne and synthetic aperture radar and mosaic IR sensors, as I mentioned before. There is evidence of a trend in the direction of incorporating the signal processor more intimately into the sensor system. This is the case, for example, in active antenna arrays for radar and communications, where high spatial resolution and rapid pattern adaptation to the jamming environment are required. Another example is the melding together of IR mosaic sensor arrays with a semiconductor array to form an integrated system which offers advantages of greatly simplified construction, increased performance, and reduced cost. An example relating more to communications applications is integrated optoelectronics, where laser sources and detectors are combined in a single substrate with electronic semiconductor junctions. The trends in radar technology are towards greater range and angular resolution to spaceborne systems. A space-based radar will pose severe structural problems, since a very large aperture antenna will be needed to achieve the resolution necessary to detect and track ground or airborne targets. As is also the case with large optical and IR sensors, it will be impractical to build radar antennas in space having the necessary structural rigidity. Instead, flexible structures will maintain the desired configurational tolerances by means of active control mechanisms, which adapt the shape to compensate for deformation induced by external forces. These control mechanisms will need to incorporate some form of optical or radio sensing device. After a signal has been collected by a sensor, it must be processed to derive useful information. This is the area which I believe will provide the greatest challenges to the electronic specialists. Recent DOD initiatives, such as the VSIC program, VHSIC, which stands for Very High Speed Integrated Circuits, pronounced VSIC, the VSIC program have opened up new frontiers in computing and signal processing capabilities, but many problem areas remain to be solved if we are to exploit this new technology fully. Let me now turn to some high leverage technologies, such as the VSIC technology, and give you some idea of some of these new initiatives in technologies which are taking place now. First, on very high speed integrated circuits, VSIC. Recent DOD initiatives, such as the VSIC program, have opened up new frontiers in computing and signal processing capabilities. The VSIC program is the centerpiece of our effort to surge ahead of our potential adversaries in electronics technology. Our efforts to date have focused on developing a 1.25, that's 1.25, micron silicon chip, which will increase computing power by over 100-fold. I'm talking about a feature size of about 1.25 microns. In 1984, 4 new efforts will be initiated. These are aimed at inserting VSIC technology into operational military systems, increasing the yield in the manufacturing process, providing computer-aided design tools to permit widespread use of the technology by U.S. industry, and beginning the effort to develop a U.S. micrometer VSIC capability. Further challenges remain in the packaging and testing areas, though we anticipate achieving the ultimate goal of the present program by developing half-micron chips by the late 1980s. Obviously, this entire area of compute and signal processing is one which will provide great challenge to electronic specialists throughout the next decade. Let me turn now to software. First, let me give you some numbers. It has been calculated that DOD will spend this year of 1984 about $11 billion on systems embedded computers, of which 80% will be consumed by software costs. $11 billion on systems embedded computers, with 80% of it going for software costs. And it's further been estimated that by FY 1990, that cost will have escalated to $37 billion, with 85% going for software costs. So you can see it is a very serious problem. As a result, there are some software initiatives which are now underway. One is called the STARS program, S-T-A-R-S, and STARS stands for Software Technology for Adaptable, Reliable Systems. A main ingredient in the technology-based defense strategy is the use of smart weapons, weapons which have computers as integral components. In fact, computers have become essential to the military mission. Almost every defense system fielded today contains a computer whose software provides a very high percentage of the functional capability of that system. Clearly, the future success of U.S. forces in a conflict will depend very heavily on the maturity of our computer technology and its applications. Our new STARS program will exploit and expand the technology base to address all facets of software, including acquisition, management, development, performance, and support. The goal of STARS is orders of magnitude reductions in the labor intensiveness of software development and evolution, and comparable reductions in the number of software defects latent in weapon systems. STARS will focus on the automated software, quote-unquote, factory concept, involving a coherent and integrated system of computerized software tools and reusable software parts or building blocks that will reduce the labor intensiveness of the software process. It will also reduce the complexity of software and enhance its adaptability. Another segment of the software initiative is the Software Engineering Institute, or SEI. Software technology has been advancing rapidly, and a broad technical foundation for software engineering exists. Notice I said software engineering, not software science or computer science, and continues to grow. For a variety of reasons, however, most of this new technology is not crossing the bridge into practice, at least not yet. The Software Engineering Institute will not be a research or teaching institute, but an organization of world-class software experts dedicated to accelerating the transition of emerging software technology to our defense systems. The primary mechanism for this acceleration will be the automated software factory concept, the pieces of which will be developed under the STARS program. I don't need to tell you how important these software technologies will be in the 1990s and beyond. Let me turn to one more initiative, the so-called Strategic Computing Initiative, and I believe Bob Cooper will say more about this later today or tomorrow, I'm not sure when. The Strategic Computing Initiative is something undertaken by the Defense Advanced Research Projects Agency, or DARPA. This program encompasses the development and application of machine intelligence technology to critical defense problems. The program calls for transcending today's computer capabilities by a quantum jump. The powerful computers to be developed under the plan will be driven by expert systems that mimic the thinking and reasoning processes of humans. The machines will be equipped with sensory and communication modules, enabling them to hear, talk, see, and act on information and data they develop or receive. This new technology, as it emerges during the coming decade, will have unprecedented capabilities and promises to greatly increase our national security. The program will produce adaptive, intelligent computers specifically aimed at critical military applications. 3 initial applications are identified in the DARPA plan. These include autonomous vehicles, like unmanned aircraft or submersibles or land vehicles, expert associates to heighten pilots' capabilities to act effectively and decisively in high-stress combat situation, and large-scale battle management systems. As with all other long-term initiatives, the program calls for a cooperative effort among American industry, universities, other research institutions, and government. It is estimated that some $600 million will be expended over the first 5 years of this program. The successful achievement of the objectives of the Strategic Computing Program will lead to the development of a new generation of military systems containing machine intelligence technology. These systems promise to provide the United States with important new methods of defense against both massed forces and unconventional threats in the future. I will just finish by saying very briefly that one of the main goals of our program is to make sure that industry, the universities, and indeed the whole federal government, not just DOD, work closely together. We have a number of programs going which we are fine-tuning all the time to improve this interaction. I'll just briefly give you some examples. One of them is the IR&D program, the so-called Independent Research and Development Program, which is a program whereby industry can charge overhead to DOD contracts, but the money can be used any way the industry wants to use it to sharpen their knowledge of technology. Under the IR&D program, we are now encouraging defense contractors to work more closely with the universities. We feel this is a benefit to everybody concerned, industry, the universities themselves, and DOD, in a number of ways, such as the faster transfer of ideas from university to industry, the better understanding by university people of industry problems, and the earlier connection between university undergraduates and graduate students with industry so they can slip in more quickly and become more useful faster in an industry situation when they get hired later on. And we have a program, we have got the word out, and we're going to encourage industry to do more of that, get a closer interaction going. Another example, the IR&D program applies to large companies. Now, the other example applies to small companies. There is a program called the Small Business Innovation Research Program, SBIR. It was passed by Congress and signed into law by the President almost 2 years ago, and it's a highly structured program for small businesses to encourage them to innovate and generate new ideas and get them out into a product. And again, we're telling small industry people to go out, talk to university people, get their help, not reinvent the wheel, and get a good interaction going. On the university level, we have a number of interactions. We have a program to fund university research instrumentation to replace obsolete and obsolescent equipment in support of research which they do for DOD or which is of interest to DOD. At a high level, we have a DOD University Forum, which is a group of 20 people, 10 university presidents and 10 DOD people who meet twice a year for an afternoon and discuss any kinds of problems that we have in common. And we have gained quite a bit of understanding doing this over the last 2 years. I think you'll hear more about this from Jordan later, about some of the DOD university interactions. And I think I've fully spent my time. I will finish at this point. Thank you very much for your attention.
Okay. Leo, why don't you stay here? Thank you, Dr. Young. The floor is now open for questions. Dr. Young, who previously served as Information Director for DOD R&D, is a good window on the Pentagon, particularly in the electronics field. So there are questions that you might be interested in posing. I'm sure that Dr. Young will be with me and attorneys to listen.
You didn't seem to say too much about standardization. It appears that almost everybody is building their own computer, especially in the Defense Department. And if I could tag on another question, is this more susceptible to EMP?
Why don't you repeat the question?
Okay, there are two questions. First one of which I'm not very well qualified to answer, but I'll do my best. The first question has to do with standardization in the computer area. Aren't there too many computers being built, and is there enough effort in standardization? If we're talking about embedded computers, then each system has to be specially designed for its own purpose, and what you need to standardize on more is the chip than the computer itself. And the VISIC program is in fact producing a number of chips right now, so-called technology insertion, working into particular systems. What will evolve from this, I don't know, but hopefully there will evolve some standard chips that can be used for other systems as well. On the software side, of course, a lot is being done on standardization. There's the ADA language, ADA, which is essentially a standard computer language, and out of which has now grown the STARS program and the SEI, the Software Engineering Institute. In other words, ADA was strictly standardization of how you write the language. The SEI goes beyond that, how you maintain it, how you update it. It's almost like a product, like a piece of hardware. And hopefully through the SEI, some standard procedures will evolve so that you have what is sometimes called P-cubed-I, pre-planned product improvement, so that as you write the software, you already allow for future improvements that you haven't got ready yet, but which you can anticipate. So that there is all kinds of things going on. I don't know of any single program to standardize. Now, the second question was on VISIC. The question was whether VISIC isn't susceptible to radiation damage, or something like that, I think is what you said. EMP, sorry. It is susceptible to both radiation damage and EMP because it uses solid-state technology. If we went back to tubes, we'd be out of the woods and there would be no such sensitivity, but nobody's talking about it. There are efforts, there are very definite efforts to provide radiation-hardened solid-state circuits.
Generated on the first couple of shots would keep one of the present generation supercomputers